FRQ Friday thing threw me off. Okay. Let me give you a couple basic examples outside of geometry. Question, why would this be considered outside of geometry? It's curved, right? If it was straight up and down, what could we say it was? A cylinder. But I'm going to tell you it's actually not outside of geometry. Not when calculus is involved, because even though true there is a curve, so I can't just use pi r squared h, I still can think about what would a slice of this look like. If I were to pull a two-dimensional slice out, what would it be? A circle. And how do we always find volumes? We figure out what the slices are and we multiply it by, wait a minute, how do you find the volume of a cylinder again? Pi r squared, what is that? The area of the circle times what? Height, which accumulates, it says take, ultimately, the two-dimensional slice and multiply it by the height, aka like accumulate it through the entire figure. Now this one, I can't say just times h, it's not that simple. But if I could possibly like define the parameters that the circle's within, guys, depending on where the circle is it going to have different radii? Yeah. Yes. However, could I possibly figure out a formula for this curve? And could I say, hey, the radius is going to be from the center to that curve, and yes, it's going to be changing, but integrals let me figure out at all these different points in between here and here. If I follow that curve and if I take all these different heights, I could accumulate all these different circles and say volume. Ta-da! We'll see an equation soon. What's another one? What if I was to give you something like, I'm trying to think what else I can draw simply. But I'm trying to do one that doesn't have a circle. Let's do harder if I didn't have shading. I'll show you some different examples in a second. But if I was to think about, if I had nice shading, I'd be like shaded and not shaded. Anyway, whatever. If I were to say, hey, I have this area, and it can be bounded by all kinds of different things. This time it was bounded by these two curves, and actually you could think about it as one curve that's being rotated. Hey, it's kind of like in a hyperboloid, but not. Anyway, over here. That's section 7.2b. If I was to think about, guys, what does this look like under here? Area between two curves, maybe? If I was to think about an area between two curves, anyway, whatever, it's confined within. And then I was to think about maybe like equilateral, okay, you should be a little bit higher, but equilateral triangles, I could say, hey, the equilateral, all the sides are equal, defined by, kept within these parameters, but then I could have an even weirder shape. And technically it'd be kind of flat on that side and kind of, anyway, it'd be gross. Let's try to think about some other ways of thinking about how if you add all these different slices together, you can get a whole thing. Is he coming? He's not coming. Go. Nope. How about now?
Oh.
That's lame. I'll just do it the old-fashioned, really ugly way. Where's the zoom? There it is. Could I, theoretically, form a raindrop by doing lots and lots of different circles? Or do a curve by putting lots and lots and lots of different squares? Or could I make a vase by doing lots and lots and lots of different semicircles? Or could I make a fishy by doing lots and lots and lots of different semicircles? Or could I do, where's another one? A moon, what are those, rectangles? I think those are rectangles. What else? There's another raindrop. There's a shark by, I think, triangles. What else? Snowman, obviously circles. For each of these are just silly, not silly, but they're student projects. just ideas of, now kiddos, hold on. How many slices are there in each of these projects? Well, there are lots, but how many are there? Finite number, right? Because there's a finite number question, are any of these going to be perfectly smooth? No. So these are just approximations of what would, is a base going to be all segmented? I guess sometimes, but is it going to be always? No, a base is usually smooth, right? So when you cut up a finite number of slices, it's going to be approximate. What else did we cut up into a finite number of and it was approximate this year? Area under the curve, and we did it with rectangles. Now we're not going to do it with rectangles, we're going to do it with areas. So we're going to add together areas, add together two-dimensional slices, and then we'll get the third dimension. How do we do that mathematically? Here, a V, a go. Oh, those are cool, but sadly my computer blocked both of them earlier. Okay. Let's go here first, then we'll come back and I'll show you what I mean. Let's get our, there we go. Now, my ones who are like, I'm not drawing that. Okay, you don't have to necessarily be able to draw it. But visualizing, of course, does help. Remember, that's why I showed you earlier. More ways to get exposure to this topic besides just me in class. I'm going to change this reference system a little bit. Let's put it here. Okay. This is my x, and this is my y. Of course, my z would be coming out. This one is my x, this is my y. It's been like put, and then z is, of course, going up and down. Just like area between, orientation is super important with slicing. And unlike area between, why is it so long? Unlike area between, with area between kiddos, could we kind of like sometimes do dx and sometimes do dy, and even if it maybe should have been a dy, a dx can usually work, it just might be harder, or vice versa. Mm-hmm. You kind of have like a choice, right? There's kind of freedom in it. These ones, there's no freedom. There's no freedom. In a sense of the problem itself will dictate whether dx or whether dy. So what's different? Instead of having little rectangles, we have little areas. And instead of dx being a base of a two-dimensional that's being infinitesimally flattened, it's going to be the depth of a three-dimensional slice that's being infinitesimally flattened. Still the same idea of flattening, because that's what integrals do. They take infinitesimally thin. But in this case, we're going to be taking infinitesimally thin three-dimensional slices instead of infinitesimally thin two-dimensional shapes. Thank you. But it's only going to be dx if, when you slice it, it's perpendicular to the x. And if, when you slice it, well, that didn't work very well. I know. It's okay. It's perpendicular to the y. That means that the depth is going to be change in y or delta y. Sorry, change in y or dy. We're getting up to our integral. The idea is if you slice it perpendicular to the x, you're accumulating three-dimensional figures, and integral is going to make them infinitesimally thin and add them all up between certain bounds. If I slice it perpendicular to the x, it's going to have a dx, because that is what my integral needs to infinitesimally flatten. And if it's going to be perpendicular to the y, dy, that's what my integral needs to infinitesimally flatten to make it perfect. Or else it's going to be jagged like those pictures that we saw. So it'll be finite instead of infinite. Infinitely many. Kiddos, real quick while you're still like drawing and playing with it. Weekend, WCC, homework 43 due on Tuesday. but we're probably starting section 7-2B on Monday, so just a heads up, if you can get some done this weekend, it'll definitely help. Ultimate Pi Day photo challenge tomorrow. Pi Day celebration Monday.